Thank you, everybody, for joining this webinar. And good morning or good afternoon to you, wherever you're listening and watching. I am Harold Bornfleet, and I'm responsible for the BESA product portfolio. Today, I'm going to speak to you about using individual patient anatomy for superior localization results in BESA. My colleague Mateusz Rozyniak is also on the call, and he will assist with questions and answers. We have a schedule for today's talk, and the schedule looks like this. So first, we will walk through a bit of background of MRI co-registration and the creation of individual head models. After that, I will try source localization of interictal epileptic discharges in an individual subject without using anatomy information. And then I will walk you through the workflow of a semi-automated MRI segmentation of an individual subject, followed by a semi-automated MRI co-registration of an individual subject. We will then use this information for source localization of interictal epileptic discharges in an individual subject with using anatomy information, and we will compare the results. And please, throughout the presentation, feel free to send in your questions. You can simply use the available questions and or the chat boxes on your screen. We will then pick up all your questions on the discussion, and Mateusz and I will try and answer them either during the session or at the end of the session. Now I think I'll switch my camera off so we can concentrate on the presentation, and let's have a look at it. So what is the difference between analyzing data with co-registration or without co-registration? An example is the analysis of auditory data. Here, we have a very good idea where our sources should localize. They should localize in the Heschel gyrus. The left side here shows a source fit with a co-registered brain anatomy, and we can see that indeed the sources do end up in the Heschel gyrus. On the right-hand side, we can see a situation where no individual anatomy is available. We will still get a good approximation, but we can only get a rough match to the real brain location. Yeah, and how do we get to a co-registration? Let us first spend a couple of minutes on looking at coordinate systems. So basically, this here is an example of a head where we are looking at external points only. So we don't have any knowledge of the interior anatomy of the brain. And then we need to fall back on external landmarks. And usually what is used is the preauricular points, the left preauricular and the right preauricular points, and the nasion. And this is called the preauricular nasion or pan coordinate system. We can also refer to it as the head coordinate system. Yeah, so the x-axis of this system is defined by the line that joins the T9 and T10, or the two preauricular points, and it's positive towards T10. The y-axis is defined by a line through the nasion that is perpendicular to the x-axis, and the z-axis is the axis that's left over that is perpendicular to these two axes and goes up out of the head close to the CZ electrode. If we know about the brain anatomy inside the head, then we can see how we can use a different coordinate system that's based on anterior and posterior commissure, so based on interior landmarks in the brain. So let's have a look at that one. So here we have the chance to use these landmarks, and you can see this brain scan here. Typically what we would use is the anterior commissure fiber bundle as one of the landmarks, and the posterior commissure fiber bundle as another of the landmarks, because they're quite close to the center of the brain and they can be easily identified in the brain scan. And again, we will have an x-axis that it goes from left to right, a y-axis that joins the posterior and anterior commissure and points to the anterior direction, and the z-axis again is orthogonal to these two other axes. Right, and what is the benefit of doing that kind of thing? Let's have a look at the influence of these coordinate systems. The thing is that we actually do have a substantial anatomical variance across subjects. This fact is taken into account to a varying degree by different coordinate systems. So let's here have a look at these red dots. The red dots are the positions of the Heschel gyrus in different subjects, and we can see that there's quite a lot of individual variance between these subjects. So maybe worth taking a quick look at. So the brains are not all the same. They kind of have quite a big variability. And these are just sort of pointing, actually identifying these knots in the MRI. So we didn't fit anything here. We just identified them in the MRI. And then if we go and plot all these positions on an average brain, we can do this by using coordinates from the exterior landmarks using the PAN coordinate system, or we can use the ACPC coordinate system based on internal landmarks. And we can see that the variability of these individuals, if we use the interior landmarks, is much less, in fact, significantly much less than compared to the exterior landmarks. So in the left side, we have the PAN, so we can see the scatter of the points. In the right side, we have the ACPC situation. And the same thing we can observe if we do the other way around. So if we take these AC and anterior commission and posterior points from the internal landmarks to the head coordinate system, and then mapping them on a template, on one template head, we can see the scattering. So again, that shows us the variability in the individual brain anatomy between subjects. So the AC point is here the blue scatter cloud, and the posterior point is the red point cloud. And also what we could maybe see is that while the scatter of the AC point is relatively homogeneous, maybe a bit stronger in the Y direction and the Z direction than the X, we can also see that the posterior point also has a wider spread in the Z direction, and that's because there's a tilting of the brain axis with respect to the exterior landmarks that can cause kind of a stronger shift if we go away from the center. Yeah, and another thing we can do if we have the individual anatomy available is to go to a realistic volume conductor. And here we can use the MRI images again. This is an example of a finite element model. So basically, you can see different colors in this MRI scan that stand for the different compartments of the model. We have the brain compartment in kind of pink color. Then we have the cerebral spinal fluid, CSF, in the blue color. We then have the skull in green and the scalp up on the outside. So we can do this directly if we have the anatomy available. And we can also do a boundary element model calculation, which again has the brain but no CSF, brain, skull, and scalp in this scenario. About the CSF, why would we bother modeling it? There is actually there is quite a lot of CSF around in the brain, especially in deeper regions of the brain, and because the conductivities are slightly different between CSF and brain tissue, the current will change its direction whenever it passes a new layer. And in this case, when it passes from brain to CSF. So maybe you can see this in this little plot here, that the CSF has a slight different direction of current. And we can also simulate what the effect will be. So if we look at localizing using finite element models, localizing activity in from different simulated brain activation, ignoring the CSF or adding the CSF, then we can see that in particular in the frontal areas, we have a lot of improvement in the model if we actually model the CSF as well. In other brain areas, the effect is not large at all. So overall, we're looking at errors in the range between maybe 2 to 7, 8 millimeters, depending on where the brain we're located. So one thing we need to do with the finite element model and also the boundary element model is we need to calculate lead fields. So lead fields are the forward models of the question, if this brain region is active, what will I measure on my sensors? So to do this, we need to have a co-registration. We need to know where the sensors are with respect to this brain region. And then we can calculate these lead fields based on this finite element or boundary element model. And then we can calculate the magnitude of the signal that any source inside the head will contribute to the sensor. So yeah, without a co-registration, we have a spherical model. This spherical model is kind of the first approximation of the head shape, and of course it's not the same as using individual boundaries of brain tissues. Yeah, we also have, as I said, a boundary element model, and that assumes a simplified description of the head geometry based on the boundaries of the head tissue. And the simplified description means that we have smoother surfaces. For most EEG datasets, that should be a good approach. So you can see some differences here between boundary element and finite element model surfaces. And luckily, with our BESA software, we can actually calculate both and then directly compare the impact of using these different models. So in summary, when should I co-register my EEG or MEG data with individual MRI data? This makes sense always when source localization is an important goal in my analysis. And also it makes sense when I want to use anatomical landmarks to create spatial filtered data. For example, if I have a group study and I want to calculate source level connectivity based on atlas locations, then it makes sense to use a co-registration so that the atlas locations can be mapped to the individual brain coins. And individual volume conductor model should always be used when source localization accuracy is a key aspect of my analysis. This is actually only partially true for MEG. I think in MEG you already get very good results with spherical models, but for EEG it's quite a crucial factor. So this was just some background, and now I want to have a look at a pipeline for analyzing spikes in EEG and MEG. Today we're going to look at EEG, in fact, and this is just kind of the general idea of how we propose to go about data analysis of epilepsy spike and seizure data. So we would first go and find the average, find and average the interictal spikes and seizures, map the onsets, and then localize the sources. And for epileptic spikes, the steps are to find a good montage where the spikes are evident, then use a pattern search algorithm to find the spike events, inspect them, maybe remove some that are not real events or that have too many artifacts, then average the remaining events, and we can then have a look at the map of the spike onset. And then we localize the spike onset and also the peak, and we check for propagation using dipoles and imaging data. So the thing that's also important for good results is to use the MRI. And here we need to create finite element and boundary element model and co-register. We need to, in order to get there, we need to first segment the head tissues, then create these models, and then do the co-registration. So today I will mainly focus on this part first. So we're going to localize the spike onset first without co-registration, and then we're going to redo the steps for going the full way with the MRI data and then compare the results. So first step is look at some spike data, and I'm going to have a look at the spike that's called basal. This is from our example data sets from the LTM section, temporal basal polar spike, and it's already average. So I'll skip the actual pattern search. It's maybe part of another lecture at some point. So we're just going to look at the average spike now. We can do a map of this, and we can see that there's a strong negativity here at the left temporal side, not so much on the right temporal side, so it obviously is more left-centered. And if I click on this map, I can see a sequence of maps, and we can see that the center of this negativity actually moves from this lower section upwards and a little bit to the frontal part. So this is already an indicator that we may look at some propagation of this spike. So now that I've done this, I want to do the next step and analyze this spike in source localization. So I'm going to drag a block with my left mouse over this data set, right click, and find the source analysis item here. And one thing to look at is that we should have the filters set as a good way to analyze this data. So one thing we can do is do a forward filtering at about 3 Hertz to get the baseline straight, and do a zero phase 35 to 40 Hertz filtering, so that the filter band actually is well outside the activation speed of the spike. And here I can say exactly which epoch I'm going to look at. So I'm going to look at something between -200 and +200, so that I'm just concentrating on the main area of activation. Then I start the source analysis, and what I can see here is a division of the data and the model. So on the left side, I see my data. The top here shows me the butterfly plot of all the channels, and underneath I have the PCA components, so principal components that are part of the data. And in some cases, I would maybe see only one main component, then I can be pretty sure that there's only one brain generator. But in this case, I see at least 2 components here. And up here, I see a baseline interval. So this should ideally be adjusted by clicking on this red thing, so that my baseline is outside my main activation. Then in the center here, I see the global field power plot that's normalized. And this gives me a chance to figure out where the onset of this activity is and where the peak is, etc. And I'm going to now look at this first part, and then I can drag over this to create a fit region. And now I can use the mouse wheel to adjust the fit region. So I think I'm going to go from, maybe move it 1. So go from -36 to 20 milliseconds. And I can see that the PCA then adjusts itself and tells me so how much activity is covered by the first component in this particular fit region. So I've got 99% of all the variances in one component. That is quite good. That means I don't have a mix of different activities in this fit region. Then the model I'm using is a 4-shell ellipsoidal head model. So the spherical model that BESA uses is not a simple sphere, but it has 4 different compartments for head, scalp, bone, and CSF with different conductivities. And it's also adjusted to match the head shape by shaping it into an ellipsoid. Right, I'll start the fit, and that'll create a dipole here in this dipole section, and directly fit it and tell me here the source waveform. Scale that up a bit, and also the residual variance, so what's unexplained in my data. So the residual variance is plotted reversely to the global field power. The higher this red plot, the better is the match. So residual variance in the fit interval is quite small. That's very good. Now I'm going to remove the fit interval and just see what the residual is, and see that still some large component unexplained. So I'm going to mark that one, and add by double clicking into any of these schemes. I can add a second dipole and fit the second dipole too. Okay, and I can see that there's a propagation here happening. So I've got my first spike wave complex and then my second spike wave complex. And this second one is actually delayed by some time. And I've now achieved a pretty good model. So if I compare residual with data, I can see that the residual is very small in comparison. So I've already explained most of the data with this two dipole model. And I'm going to save this model so we can later use it again. So the name of the data is this one, and I can call add temporal to the spherical model. Okay, so that we'll remember this model, and now we want to actually use the individual anatomy to try and see if we can get a different fit, or what the difference will be if we use an individual head model for this. To do this, I first need to go and actually do a segmentation of my MRI data. So here we have BESA MRI. So BESA MRI looks like this when you start it. It's a standalone software that directly interacts with BESA research, and it's a workflow-based software. So we have basically two workflows available. One starts the segmentation and one starts the co-registration. I can only do a co-registration once I have completed a segmentation. So let's do this first. Segmentation first asks me here to tell me the goals of my project, and I can also load T2 MRI data in addition to the T1 data in case I want to have it available, and it will give me a better modeling of the bone layer. But it also works for just T1 MRI data. And if I want to use a finite element or boundary element model, I need to check these boxes, and then it'll automatically create this. Also, I can use a cortex inflation if I'm interested in visualizing cortical results on an inflated cortex. Then I go on next, and then I can load my T1 data. And my T1 data in this case is actually a data set that was already processed by Brain Voyager. So it's a Brain Voyager VMR data file. And we can also load DICOM data and analyze nifty data. So we have various options available for loading different data formats. I think mainly people will use DICOM. And I'm going to work with this this one first, and now I need to give this patient a name. This will, if it's a DICOM dataset, it will read the name automatically, but in this case, I need to supply it. So we'll call this 10 days demo. And then I can go to the next step by simply pressing the Enter key or the space key. And one thing that is particular with Brain Voyager datasets that I need to confirm the orientation, and that is correct here, and the left and right correctness. So I can just move over this and then go to the part that now I would also need to do for the DICOM datasets. So for DICOM datasets, I would not need to set the orientation, but I now have the task to find the AC point in the data. And the AC is where the anterior commissure separates the two brain hemispheres. And this is kind of at the bottom of the corpus callosum. So if I navigate here into this this area and then go to the left side and use my mouse wheel to go scroll through the slices, I can see quite nicely how the anterior commissure comes up here. So I place my mouse exactly over there, and the crosshair goes over here, and then I can set this AC point. And the next task is to set the rotation. So I want to make sure that the axis of the brain really separate the hemispheres. So I can go down to the lower levels and change the rotation of the brain like this. And then I can go to the next, to the middle section and change the rotation. because this one's already pretty well aligned. And the last rotation is done in the right side. And here it's important that I find the posterior commissure, which is just the top end of this structure here, which, if I find it, will point out this fiber bundle in the left bottom layer. So I rotate in the right layer until I see it. Now I can't see it, but now when I get here, I can see it appearing here, and then I can set the rotation. So now I've already got my brain axis aligned perfectly, and now I just need to point to the position of the posterior commissure, which is here in the left side, and set the posterior commissure point. Then I can go to the next work step, which is to set some Talairach transformation markers. And here the aim is just to find the boundary box for the brain for the Talairach transformation. And this is done by using a mouse wheel again. So first I concentrate on the anterior and posterior points. So I go until I see the brain gyri appearing, and press the space key or enter key to move to the next point. Then the same with the posterior point. And then I go to superior point, which is visible on the left side using the mouse wheel. I can go up here and to the inferior point, which is round about, you can see just the temporal lobe is always the lowest structure, and where the temporal lobe just begins here, I can set the inferior point, which leaves me the right and left points. So the right point is round about here, and the left point is round about here. Now I've found my box, and I then go on to the next block step, which is to set some markers that will help the automated segmentation process. So the markers would be the nasion. They don't need to be very precise in this scenario. It's just to align the brain mask for the segmentation. The next one is the inion. So the inion is round about where the cerebellum and the cortex disappeared. You can go along this line. Then you can see this black structure. This is the bone where it kind of protrudes. So inion would be round about here, where the protrusion of this bone gets larger. And then my brainstem markers are just some calibration markers for the segmentation algorithm. So I need 3 to 5 points in here, which I've just set. Press the space key again. And finally, I need to tell the program where to cut off the 3D reconstruction of the skin that we'll later use for the co-registration of the electrodes. So this is important that we have it not in the black area, but that we actually have it in an area where we have MRI signal. And then we can also move this up and down if we want to. Okay, this was a bit of manual interaction, but the rest of the segmentation is completely automated, and I can now start the automated finalization, and this will then go through these steps. And these steps will now would now take about 15 minutes. So since we don't want to sit here for 15 minutes waiting, I have yesterday run through the whole thing, and I can now cancel this thing and show you the final result so that we're a bit quicker. So if I cancel it, it'll just take a little while. Okay, so this project will now not be saved, and instead I'm going to open the final result, which is this one here. So if I open a finalized work step, finalized MRI, it looks like this. Then I have the chance to view my results, and I can see the reconstructed skin surface as well as the in this case inflated cortex, because I also did the inflation, the reconstructed white matter gray matter boundary of the brain, and yeah, that's it, the skin. And also I have the FEM surfaces that were automatically created. So this is the skin surface, bone CSF layer in blue, and the brain for the finite element model. And the same was done for the boundary element model. So here I have the smooth skin surface, the smooth skull, and the smooth brain for the boundary element model. So all these are available, and I can now use this information for the co-registration and finite element lead field and boundary element lead field computation. So I'm going to show you how that works as well. So I close this project and go back to my data set, which I now want to co-register. And this will be done using File and then go to the MRI co-registration point here. And if I do this, then I get asked to save my surface head points. So in this case, I have digitized head surface points, so I can save them to be used for the co-registration. And then I get into the second workflow in BESA MRI automatically, so you can see how it was automatically brought up. And here I have some options. So one thing I can maybe show you at the end of this webinar as well is I can also place electrode system if I don't have digitized information. And then, of course, I can tell the program to generate lead fields, so finite element and boundary element lead fields for the EEG analysis. Same is possible for MEG if I have MEG data. So I go next and then next again to select my input project. So this is the MRI that I've just segmented. And the next step here is, so initially when you do it for the first time, you need to supply coordinates for the 3 preauricular points because they are important landmarks to match the electrodes to the skin surface. And so I can do this by moving this suggested position around on the head surface until I have matched the nasal position, and then press the space or enter key. And then do the same with the left preauricular point and the right preauricular point. If you have digitized these points during the recording, of course, it's very important that you find the same points. Some people digitize in the ear, some people digitize in front of the ear. So this needs to match what you digitized during your acquisition. Okay, and then we go to the next step, and now we need to select the file that we just saved from BESA Research and open it. And we then get an initial match of the electrodes to the head, which is not particularly good, but we haven't actually done the surface fit yet. And one thing that I would also recommend here is that you have a look at the electrodes. So some electrodes will be disabled from fit, which are the kind of transparent ones, because they are too low, and the low sections, especially in the front and the face, they are prone to changes in so they're not very reliable, so they will not be used. And this one I will also not use because we don't have the MRI information at that point, so I'll disable that one for the fit. And then I can run the surface point fit to get an improved result. And here I can still try and optimize this fit a bit more by moving the electrode cloud a little bit, a few millimeters to the back, and then I can see how I've got a much better match of my electrode cloud. So now I'm happy with my result, and I can go to the next point. And the next point is to run the lead field computation. And again, this will take quite a long time, and I can just show you how it starts. And then we'll skip that step as well and work with the prepared co-registration results that I did yesterday. So the initial part is to initialize the finite element model calculator. Then each electrode will be calculated for the finite element model. You can see it starting here with the first electrode. And then go through all the electrodes, and then it'll also do the boundary element model computation. So that can take maybe half an hour or so. And the good thing is that this can run totally independently, and you can just pick it up and it's ready. And yeah, for the segmentation of the brains, I forgot to mention that you can also prepare all the landmarks for several subjects, and then you can batch run the whole finalization of the projects overnight, for example, and then have everything ready in the next morning. Good, so I'm just going to cancel this computation and not save this, because we already have a finalized project available that I'm now going to use. And for this one, I just go to our file, head, surface points, and sensors, and here I can load coordinate files. The shortcut for this is Control-L, so a very useful shortcut. And here I can actually now go to the Coregistration section and browse for the file that I created last night. So I'm just going to work with this one. And I've got the green checkbox, that means everything is in order. Press OK. Right, and now I have a co-registered data set, and I'm going to do the same analysis again. So basically go over this data here, right click, and I can even use exactly the same settings for source analysis that I did before, and open the source analysis box again. I'm just going to do one more time the adjusting of the baseline so that it doesn't interfere with my spike peak. And look at my onset interval. So if I go to the edge of this interval and use the mouse wheel, I can adjust so that it really matches the onset. Again, I have my 99% and press start fit. And now get the first dipole fit result. But this was actually using the ellipsoidal head model. So I didn't want to use this one, but I actually wanted to work with the individual head model. So here I need to choose my head model. So let's try with the individual FEM and redo the fit of the same fit interval. And now we can see that it actually moves and goes a bit deeper than before. And just like before, I will have some residual that I don't want to neglect. So I just again go over this part of the residual so that I get little interference with any other components. Double click to add the next dipole and also fit the second dipole here. And that goes more interior now and has a totally different orientation. So let me have a look at the map first of all. So if I double click to set a cursor and press the M key for mapping, then I can see the map appearing now on the individual head that I've co-registered. And if I move the map cursor, you can see how this map changes, and you can see how the different sources become active. So this is the second source now active, which has a sort of more radial orientation and shows this radial type map. And before I had the first source active, and that has a tangential style map with two maxima. So now I've got very nice decomposition of these two signals, and I can also show that in the anatomy, pressing the A key for anatomy, and see where in the anatomy this actually resides. So let me just make this a bit bigger. And another thing that we can see now here is that we have the confidence limits plotted. So okay, make this, if I increase this one. Yeah, so you can see the confidence ellipsoid being plotted. So this gives you an idea of what is the likelihood that the source is really in this particular spot. And if I have a very good signal to noise, then I usually also get a very good confidence limit estimator. And if I want to visualize the 3D brain around this, so I've got this option here in the toolbar that toggles the brain surface on and off, and I can use the shift and up and down keys to make this more or less transparent. So that can give me quite a good idea of which brain section is actually really responsible here for the onset and also for the propagation. So propagation disappears a little bit in the brain, but it's also visible here. Okay, so I go back to my plot here, and I will now label these. So this was onset FEM. This was peak FEM. And now let's just switch these off for a moment and have a look at the boundary element model instead. So I'll switch my model to boundary element. Okay, this is going to have a slight adjustment of source positions because the boundary element model has a slightly different source space available. So source is maybe moved by a millimeter or so, but it'll still be more or less the same. And now I want to add another source and model this one for the onset interval. In fact, I can use the same interval that I've remembered here and start the fit for the band model. Yeah, so we can see the boundary element model is the same depth, but it's more lateralized compared to the finite element model. And also, let me add another source and fit this one for the residual. So we can see this goes very medial here, and yeah, so the locations are actually a bit different from what we had in the finite element model. Let me just switch them off again and on again, and refit just to make sure that the source didn't move. Refit this one to the same interval. Yeah, it had actually moved because of the boundary element model. So this is a real comparison now that I have between the finite element and the boundary element. So the initial sources are close, but not very close. So there is a difference for sure between boundary element and finite element. And now I can also load the model I had done earlier. So append the solution for the manual fit that I did. This was this one I just did 10 minutes ago for the spherical model. And then we can see that the spherical, let's just compare the onset sources for the moment. So my three onset sources are for the finite element model and the boundary element model quite close together, and the dipole that I fitted for the spherical model is actually quite far away. So it's much more superior in a different brain area compared to my finite element model. So in this case, it's especially if we go to some deep sources or low sources like at the temporal lobe tip, it's quite important to have accurate head models to get a good localization results. Even though, okay, to not completely put down the spherical model, we also have to say that all of these ended up in the same brain sublobe. So that is one thing we can achieve. But if we want a real accurate source localization, we should go for a realistic head model. Good. And then I just wanted to give you one more idea of what we can achieve if we don't have digitized information available. So let me just open one more example data set. That is the in my recent list. Recent files, child 6. So this child 6 was a child with epileptic discharges, and if we want to do a realistic head model, and we do have the MRI of that subject available, but we don't have digitized electrodes, this would be the scenario here, that if I view these head surface points, you can see that put an S for sphere. You can see that the spherical model is just a sphere because we don't have any digitized coordinates here, and we have a default head radius of 85 millimeters, so which may not match that child very well. But what we can do then is to initiate an MRI segmentation, and we then go to the MRI co-registration again. And we get an information that we have spherical coordinates, but we will just be stubborn and yes, okay, we're going to retain these coordinates and save that file and then go to a co-registration workflow in our BESA MRI. Yeah, and now it's important that we tell BESA MRI that we're not expecting it to fit these electrodes, which have only a spherical coordinates, but to place them on the using the 1010 electrode system to place them on the reconstructed skin surface. And then we go next, and we can select our input project. And now I have to admit, I don't actually have the individual MRI of that child, so but to show the concept, I just use my own MRI. And we're going to walk through this. So we now have the section again where we need to define the nasion and left and right preauricular points. But as you can see, I had done this once before, and if we've done it before, we don't need to redo it. We should only redo it if we have a digitized sensor array that was digitized with different LPA, RPA points from the ones that we put here earlier. Okay, then we go next and next, and we pick up that file that's saved. And now it will actually replace this file. These coordinates will be replaced with the ones that BESA MRI sets for the electrodes on the head. This is a very quick procedure, so we've already finished. We can see that this surface point fit will be meaningless. It will have zero error because we just place the electrodes on the head using the 1010 strategy. So we started from CZ, worked down to 20% and 10% directions using fiducial coordinates, and basically putting our tape measure over the reconstructed head. And that's a very easy thing. So we now already have finished it. And if we go back to the data set here, we can now see that our point cloud is no longer on the sphere, but is actually on the real head. In this case, my head, but if we had the MRI of this child, it would be on the real child's head, and we can then directly go and get much better results for our source localization. And actually, this also brings me to the end of this webinar. I'm just going to go to the final slide. And I would like to mention our scientific contributors to these projects. This was Matej Troziniak, who's also part of this webinar as a panelist, and will answer questions, or maybe has already answered questions. And then also Jayan Cho, Benjamin Lanfer, Avinash Pant, and Carsten Wolters, who were all instrumental in supplying the finite and boundary element models. And Michael Shirk, Patrick Burke, Nicole Ille, and Dieter Weckesser were all instrumental in putting together the source analysis capacities and the spatial filtering that is needed for analyzing these data in source space.